Okay, so welcome everyone to this new stream of EagleFly, the experimental debugger. Today we will continue searching for the item that I think that was the last thing we did. And, and the reason that we do this is because with I mean it's like the kind of the most important thing to know if you wanna try to program, well, that that's one reason, and the other reason is because uh, we probably and we surely will need to address. I mean, we at least have to have a through understanding of how does the x64 and x86 architectures work, so that we can at least read assembly language and understand what's going on inside the computer. Because if you think of it, I mean, let me go to open the project. And if we see, I mean, right into the places that we call, right, even though we use Windows to set up these kind of events for us, so that we can handle them in a high level manner as C and C++ could be. It doesn't matter, because I mean everything inside, everything in the deep level, it all works on a microcode and assembly instructions, which are the things that the processor itself executes and loads from memory. All the binaries are basically that microcode instructions, and probably even not microcode but bytecode instructions. They're already decoded. Well, no, well, I don't think so. I don't know. Sorry. But yeah, I mean, the point is that there's instructions there that we, if we do understand what's going on there, if we can do some kind of a, uh, some kind of parsing there, some kind of parsing thing, so we can like have a more thorough understanding how we can process each like instruction, you know. So we can, for example, if we go to, let me run this stuff, because I mean also something important is that as debuggers, I mean the debuggers work mainly on assembly language. That's what they do. So even though that, for example, we saw the breakpoint and they show us like some kind of this high level feature of showing us the source code, that's something that it's extra, and it's not the essential thing. I mean, it's not the thing that's really seen. The thing that happens really is that we set a breakpoint in an assembly instruction, such as this. So here we go. This is assembly, and this is where the breakpoint really is. This is instruction that is gonna, here's the instruction pointer. This is instruction pointer that is gonna execute. And as we see, I mean, throughout the things that we have done to today, we know that this Visual Studio Debugger, what it needed to do to set the breakpoint was to modify this instruction right here. This instruction was modified by the debugger so it can set a CC instruction there. And basically what he did was just like to mask this instruction with a CC this interrupt debugging instruction, so that it break up here and he could show us all the code inside until that step, until that instruction, if that makes sense. And so, and that's it. I mean, it's like, this is all the thing. I mean, this is the debugger itself, if we can see, I mean, if we can do this, if we can display the microcode and show it to the user, I think that would be like a really good starting point, you know, like going step by step. Okay, this is now the next instruction, and you know, like this kind of utility here, like step over, that we can go and go each instruction, each one, showing up special data there and stuff like that, and you know, like all this kind of fine detail stuff that really, I mean, the thing is that the debugger itself can understand. I think we can go and we can do a pretty good job on displaying this kind of stuff, you know. And later we probably want to care about, of course, about what happened there. Well, I think it was a jump or something. And later we can think about implementing source code visualization, stuff like that, you know, which I think is also important, but it's not like it's not the essence of the debugging, if that makes sense. So yeah, I mean, you know, I mean, this right now, I mean, for me at least, it doesn't. I mean, I don't understand, for being sincere with you. I don't understand assembly language at all. I do understand some kind of structure. I mean, I know here this is moving some kind of from this addressing memory to these. Oh no, it's moving from this register to this addressing memory, you know, and this is moving from this register to from this addressing memory to this register. I do understand that kind of stuff, you know, but I mean, if I like kind of have to like go and try to make sense of it, like, hey, well, where this is the place where we start doing this stuff, you know, it's like whoa, hold on. This is a jump here, jump equal, and this function call, I guess, women, some kind of offset from women, and then there's some kind of this is a call explicitly of a function, you know, and this is the address, I guess. So yeah, I mean, there's a lot of stuff to understand and to dig in, so we can do this stuff, you know. So yeah, I mean, I think what we would like to do before anything else should be to continue reading the ISO, as this is the essential thing to go and to continue with making this debugger. So yeah, I guess I would like to go where we stopped. That was at well, this is like kind of a historic thing, but the real place where it starts is right here. We read all these kind of modes of operation. That's basically the essence of how the IA32 works. It has two modes. Well, it has three modes, but I mean, well, actually, it has more, like 5 modes. Well, 3 modes and 2 sub modes, I guess. The 64-bit mode, sub mode. And this is the environment for the IF32, and we have the environment for the x64 or 64-bit, which is this, which basically, I mean, is kind of the same, you know, but at least from the environment standpoint, the only thing that changes is like the size of the registers and the size of the address space itself. other things they are keep it basically the same. Now we have to see the execution itself so we can understand a little bit more. For example, memory has this kind of three models that they are kind of important. One is like the really basic flat memory model where you just like have this linear address space, and in from 0 to 232 addressable bytes and to 232 power. Yeah, and we have segmented memory mode that basically it works in segments, and it can be pageable or non-pageable. Basically, the flat and segment memory models both can be pageable or non-pageable, and that's just like tells you like if you have virtual memory or not. And basically, I mean, the essence of segmented memory model, or the reason that we could use it, is because that prevents you to overwriting some kind of other segments that mean something different to you or as the programmer, where you store different data or things that you shouldn't relate to other segments. For example, if you have a stack, you don't want to mix that stack with some kind of code instructions, you know. So you have you prevent that using this kind of segmented model. And the real address modes is just a kind of some kind of extension, so it's some kind of compatibility for the 8086 processor, which is some kind of segmented because it's segmented, but it's all fixed. They are all segments, fixed segments that I think they are 64K, yeah. Now, one important thing is that, I mean, I don't know what I don't know what Intel mean by transparent translation or transparent. When something's transparent, I don't know what does they exactly mean by that. But we'll find out. Okay, so 64-bit mode architecture handle it the same way with PAE, even though they have 64-bit address space. They use this PAE. Okay. Oh, okay. No, I get it. Well, so does that mean that the code segment, I mean, all the segments that we got from, well, those registers, sorry, define uh, when we use like summon model for memory address space? I mean, does that what they mean when they use the registers for code segment, data segment, and instruction? Well, I don't know if ES and SS. Okay, cool. So segmented and real address modes are not available in 64-bit mode. And multiple individual tasks can use different memory models. That's crazy. Okay. Okay. So when using a 32-bit addressing, a logical address or file pointer consists of a 16-bit segment selector and a 32-bit. Yeah, because that's all they need for a 16-bit to. It would be something like 65536, if I'm correct. But they just need to have like 16,000 or something, probably less. Instruction prefixes allow temporary overrides of the default address and or operand sizes from within a program. So we can use prefixes to define the sizes for address and operands. Okay, that's interesting. Which I don't know what they mean by operands, but I think it's like the instruction. Well, it's not the instruction, but like this whole thing, like the instruction plus the data that where it is working on. So let me see. Okay, so we can use assembler directives allow the default addressing. Allow for addressing an operand size to be chosen for program. However, the maximum level of 32-bit linear address is still 2 to the 20 minus 1 to the 20 power. Okay, this is really interesting. So an effective address calculation uses a 64-bit base and index registers and assigns the displacements to 64 bits. So there's a base. So for example, the instruction LIA, before adding the full 64 segment base, the base is never so the base is never truncated regardless of addressing mode in 64-bit. So they are, for the move instruction, there is some kind of you can use displacements and immediates that I don't know what they are, but let me see. So we can 0 extend 16-bit and 32-bit addresses. Calculations to form 64-bit addresses. Okay, so we have here something interesting, and it's canonical addressing, which means that basically all the bits that they are in use for making effective addresses, they should be zeros or ones. depending on the most significant bit set or used. If they are not canonical, they should set an exception, a general protection exception. So probably I guess that an implied stack reference should be some kind of addressing that points to the stack. That makes sense. This includes push and pop. And instructions using RSP and RBP. So I guess that RSP and RBP are stack specific registers. I mean, you can put whatever you want there, but yeah, that will be specifically for stacks. So every time you use SS with a stack register, we will always get that SS. Even if you don't use it that way, you would get GP. And depending, but in 64 you only use FS and GS to produce GPs if you override the segment prefixes. And for compatibility or for other kind of modes, you can override any kind of non-SSX segment prefix and you will generate a GP, I'll assume. Yeah, we will need to test all this stuff, you know, because believe me, I mean, this is like a whole read, but I mean, reading is not gonna stick to myself, or at least for, I mean, I don't work that way, you know. I mean, probably yeah, it sticks sometimes, but I would like to like write some assembly program and see. I mean, all this kind of testing, and probably we can do it for the tests that we have right now, so we can see thoroughly the instructions and what are they executing and whatever. So the eFlex allows for limited control of the processor. That means that we can have some kind of certain control for what the processor is doing. And we have an application, well, that's for application levels. And we have a register that we already use in our debugger. That is the EIP, which basically has the instruction pointer. It's a 32-bit pointer. In a 64 it's the RIP, but basically it's the same, yes. It's 32 bits more. Sorry. Oh, okay, okay. So they have operands for address calculations that basically you can you can operate on addresses, and that's kind of the interesting part. You can rather, I mean, because, well, I don't know, but probably the yeah, probably they do, but I mean, in essence, you don't care about. I mean, if you see a value, you don't see. I mean, probably the 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 processor doesn't care about if it's an address or it's an arithmetic operation, probably, and it just do it the same way. Although I don't think so, because probably this implies that they are different in the way that they are being processed. You know, I mean, address calculations, they have this little difference for normally what arithmetic operations should do. And we have AAX, B, C, D, and ESI, and EDI, and EBP, and ESP. Okay. Okay. So the ESP holds the stack pointer. So basically ESP. I'm sorry. So that makes sense. See? I mean, that's why we most of the time we see EAX like a lot of times in assembly language. You know, I mean, you see here, you can see RAX being like kind of fetched a lot of times, and I mean, there's a lot of moves from memory back to the RAX. And for example, this is RSP, and RSP is from the stack pointer. So this is an offset from the stack pointer, 68. So that means that we are moving from the stack 68 in hex to get the data that's in there, and moving that memory to the register so we can operate on that. And this is another register. We're moving from the ARX, and we're moving on to memory. No, sorry, please. And this is basically, this is from RAX to back to a stack pointer, you know, and now it's on another offset, you know, now 100H, 100 hex, and then we're moving from the 100 hex back to the R8, which is, that's in 64, isn't it? Yeah, it's R8 that we are about to look at. But man, oh, that now it's like, oh, it's making sense. Oh, it's making sense, because there's a kind of coding, I mean, there's a kind of way of doing it, you know, there's a code that has to be respected, and it's like, yeah, I mean, generally this is the way that it works. This is a register to stack pointer, and we use offsets to move into memory offsets to the register itself, and that's all. And here something crazier stuff, but we're gonna get to there later. And yeah, registers to stack, that's all it is. 68 hex, 100 hex from RAX, and this is like the kind of type, you know, although I don't know, probably this is kind of a casting stuff. I have no idea. We'll have to look at it. So if we are here and this maps to this, whoa, how did we get there? Probably was a lot of time there. So we're moving out from RCX to RSP and moving on from the stack. And this is moving to RDX, and RDX is an IO pointer, okay, and RCX is a counter for string and loop operations. Probably we're in a loop. Well, yeah, we're in a loop. I mean, this is a special situations, probably they're used for something different, but this is for the stack, and this is for the IO. This is for a counter for loops. So probably it's like this kind of index that we always set into it, isn't it? Although we're not, well, probably because IFF0H is 496. Okay, what's that? Type a comment. Hello. Hello, RSP. I didn't know that I could do this. What? That's crazy. Okay. So yeah, I mean, you see, I mean, it's not even difficult to read this kind of stuff. You just have to polish and just get used to it, I guess. And you know, there's kind of caveats there, but we will get not caveats, but there's specifics, you know, about what's going on here. And the good thing, I mean, this is a compile with no optimizations at all. So that means that we can take a look at basically the raw data, you know. I mean, this is the thing, you know. And that's good. So for this is area X. That's the counter for grabbing up stuff, which is basically the same thing. But this is ECX, but this ECX is for, if I remember, loops. Okay. Uh, 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 okay, really cool, really cool. This is going really, really emotional, you know. This is, well, not, sorry, not emotional, but really, really amazing, you know. So we have accumulators. We have uh, generally ABX is more for pointer to the data segment. So this is a pointer to data which is in the segment that it's pointed to by the DS register. Okay. So it's like some kind of special thing there going on. So there's a difference between what a segment is and the register itself, because register is basically the hole where store you can store segments or pointers. It doesn't matter too much. The register doesn't care at all. It's just like, hey, you want to store here whatever you want. So you can store segments, or you can store pointers to other part of segments, or other parts of memory or whatever. As shown in figure, blah blah blah, and there's this kind of cool compatibility with the 8086 processor and the Intel 286. So the cool part is, yeah, you can reference it with the names AX, BX, CX, DX, BP, SI, DI, and SP. Cool. And that's if you just needed to address some kind of with 16-bit pointers or 16-bit data itself. So okay, cool. High low, high low, high low, high low, high low, and then this is BP, SI, DI, SP. So I mean, basically it's the same. I mean, it's like kind of a predecessor thing. Just I mean, it's kind of a, it follows kind of, it constructs for from the past. I mean, it doesn't change too much. It follows certain rules and certain names specifically. Even though, I mean, that's really nice because that means that yeah, I mean, probably the architecture probably can be, it can have its specificness for each one. uh, you can track and basically trace from backwards. I mean, if you understand some kind of architecture from the past, it's not gonna be really hard to understand some future architectures, if that makes sense. In 64-bit mode, there are 16 general purpose registers and the default operand size is 32 bits. Which that means that there are twice as much more registers. And the operand size is 32 bits, which is twice also. Well, it's not, it was twice? Yeah, I think. Well, it's twice to the 16-bit mode. Oh, cool. So for referencing R8 to R15, we need to use REX prefixes and also to generate 64-bit operand sizes. Okay, so that means that, I mean, across transition, I mean, if we are like kind of a transition between modes of processor modes, it's gonna be bananas, you know. Well, it depends. If you go from 64 to compatibility, it's gonna be okay. But if you go from 64 to compatibility, then to legacy or real mode, and then back to compatibility, then to 64, then banana is gonna be the real thing. And probably that's because of the way that registers are processed whenever you change from processor mode. So basically this is a table that gets used to the one that we got, basically from bytes to words to double words and then to quad words. That basically, I don't know what rex are, but uh, they are like extensions. Oh, the register extensions. Okay, so they're like these kind of register instructions, and you can get back until R15L, I guess. And for words, it would be the same. You have A, B, C, D, A, B, C, D, and then you have the ISI, BP, and SP. That's normal. And then you get the R8 to R15 with words. And then you can get from the normals, from IR32 you get normal EBP, and then you can get from R8 to R15 words, and then you can get I mean for quad words doesn't make sense because you need to have the register extensions enabled. Okay. So does that mean that, I mean, we have 16 registers in 64-bit, and if we use register extensions, we will use, for double words, we use just the low 32 bits for each of one of the extras ones, you know, because that's which it has here. And the same will be for the words and for the in the by ones. We just use, for the extensions, we use this little the specific size for each kind of register. An instruction can reference legacy high bytes, for example AH, BH, CH, and one of the new byte registers at the same time. For example, the low byte of the array-x register. Legacy low bytes AL, BL, CL, DL, and new byte registers at the same time. For example, the low byte of the R8 register. The architecture enforces this limitation by changing high byte reference. Okay, so it automatically changes the reference from those high bytes, sorry, to the low bytes from the other 4 registers that are on the bottom part: RBP, RSP, and RDIR and RSI, which are these basically: RBCD, RDISP are these ones. Okay, that's interesting. When 64 remote operand size determines the number of valid bits in the destination region and purpose register. So if you use 32-bit operands, they generate 32-bit result in the register, in the general purpose register, with a 0 extended to 64-bit result. That's interesting. Uh, so what does that? So what did they say before, that they were preserved if they were like in? Oh, okay, okay, okay. Ah, okay, okay. I didn't read this specifically, but only these registers, because these registers are only available for 64-bit mode. Those are preserved, but the ones that are not preserved are the ones that are used for comparability and the basic ones, from EAX to RBP, or REX to RBP, I guess. All those are not are not saved at all. So that's important. Okay, so I think that will be good for today. It was something really interesting. And man, we are just starting, man. And this is getting really, really fun. Okay? So, yeah, I think that's it. If you have any questions of what we did, well, of we what we read today, please ask them on Twitch or on Twitter or on YouTube, and I'll be happy to answer them. As for today, I think that will be all. And yeah, I think we will continue on reading uh, the IS-32 architecture. And yeah, I think that's all. Thank you very much for coming, and I will see you all on the next stream.